conference organizers for being willing for me to present this provocative talk. And the reason let me see, how do I make it full? The reason I intentionally want to be a little provocative because we have a sort of unusual state of affairs in information theory in which the quantities we care about, probabilities, are summarized by an average on a completely different scale, entropy. And I think this is where a lot of the confusion comes for biologists, engineers, and others outside the field in trying to understand our work and make use of it. And so the talk is sort of centered around taking a little bit different look at the work of Shannon and Salas and translating their results back to a probability, which is where we have a lot of intuition about uncertainty. So we're all familiar with the arithmetic mean of the log of the probabilities as forming the function of entropy. But how many of us in our work have translated that quantity back to a probability and recognized that the average probability is the geometric mean, the weighted geometric mean of the probabilities? Furthermore, when we do cross entropy, we're comparing two distributions, and we're familiar that we should take a different weight on the logs. But how many of us are aware that the average uncertainty between the model and the data, for instance, is the weighted geometric mean? So I want to sort of take a look at this framework and try to reduce some of the perplexity in the process. Now, this problem gets even worse once we start to try to ask the question, what's the variance of the probabilities? It's a complicated function that doesn't translate well back to probabilities. However, Salas's work actually gives us a much simpler framework to think about the variation of the probabilities. And so I'm going to use that as I proceed. My perspective on the Salas entropy is to define it in terms of the degree of nonlinear deformation in the entropy. And I think I'll just say that for now, given the sort of abbreviated time, but we can talk about this more later and show kind of the results of that. So I have a deformed logarithm now where the logarithm is raised to a power that I call the coupling, or the nonlinear coupling, and then it's normalized. The red curve, let's see, is this, which one is the red one? I'm not seeing red. Well, anyway. The red curve is the Shannon, is the traditional Shannon, thank you. The red curve is the traditional Shannon entropy, which is the negative log of the probabilities. And I'm going to use this work in terms of evaluating algorithms. So I think of the probability here as being what I reported for the true state, and then the surprisal as being my cost of making a mistake or a bad estimate of the truth. Now, I'm going to use Salas's work to deform those logarithms where if I have a negative coupling parameter, the cost goes to infinity higher. And I'm going to use that as a robust measure of how well the algorithm is working. In contrast, when the coupling is positive, it's going to lower my valuation of information, keep things finite, and this is more like the cost that we would put on a decision, where we know we might make a mistake, but we don't think of that as an infinite cost. So now proceeding, I'm going to do the following. I'm not going to work in the entropy domain, which is confusing and we don't have a lot of intuition about. Instead, I'm going to take my coupled surprisal. I'm going to take the arithmetic average of that to get the coupled entropy. But now I'm going to do one more step. I'm going to take the inverse, the coupled exponential, and lo and behold, the function I get is the generalized mean. And can show that in the backup slides. We have time. But here, you know, at the heart of Constantino Salas's work is the generalized mean of the probabilities. And that's really the story I want to kind of emphasize. And from that framework, I can get a lot of depth of understanding and intuition about analyzing algorithms. So let me skip a little bit. So there's a lot of literature on proper scoring rules. And a proper scoring rule is one in which if I maximize that, I basically am reporting honest probabilities about my belief. And there's a broad class of functions that do that. And in fact, any entropy function you start with can be translated into a proper score by essentially subtracting out the bias. Now, on the other hand, the logarithmic score also has a second requirement of it being local, in that you're only counting the costs of the true events that actually happened. And for the logarithmic score, essentially the bias terms cancel out, and you're going to use as a scoring rule the negative log of the reported true events. In contrast, with the Salas score, there is a bias, and so we have the local scoring rule here with this deformed logarithm, but now we have a bias that is essentially, you can show that it's related to the amount of risk. And so what I'm going to do actually is I'm going to focus just on this local scoring rule, but I'm going to accept that this is a risk-biased estimate of my probabilities. And I'm going to develop this into a curve that I refer to as a risk profile of how well an algorithm is working. So let me orient you to the curve a little bit. First of all, again, I have taken this analysis about scoring rules and I've translated them into average probabilities. And so my scoring function now is the generalized mean of the true state probabilities. And on the x-axis is my degree of risk bias, which I'm measuring with the Salas parameter translated. I use this coupling term, 1 minus q is what it's equal to in terms of the q Salas parameter. So I now can, the blue curve represents my Shannon information metric, and I want to maximize the probability there in order to have an accurate algorithm, a model that accurately reflects my uncertainty. But I'm going to bound that now with the Salas entropies. On the green one is going to give me a decisive metric, where this is often useful if I just want to make a decision. It'll give me separation in the probabilities. But if I care about decisiveness, what I've been trying to advocate to engineers is that you should also pay attention to the robustness of your algorithm. And I'm going to use the negative coupling, the red curve, to maximize how robust. In other words, I want, if I'm testing with a data set, I don't want too much fluctuation because something different might happen out in the field. So when I use this, now I'm building an algorithm that reports 3 probabilities rather than 1 probability. And you can see sort of this in this example of a handwritten numerals, the effect of this, where the green ones are really reflective of the way most algorithms are designed today. They're designed kind of to be decisive because that's what people think is better. And you can make decisions on it, but it does not give you an accurate reflection of how much uncertainty you have. So the blue ones are designed to give you that accurate uncertainty, and the red ones, though, deviate quite a bit more, and they kind of give you a warning or indication of risk. And I thought it was particularly interesting. It kind of highlights the difficulties in that the 6 and 9 are just the inverse of each other, and they're more difficult to separate. So it looks like we have just another minute. And so just digging into this a little bit more, is another sort of toy example to show how you can use this tool. Here, I'm starting with Gaussian data and generating samples for 2 classes. And I want to build a model of that. And in this case, I'm using 10 features or 10 dimensions. And my model is going to be Gaussian also. But it draws out a point here that actually, because of the uncertainties in estimating the means and variances, the Gaussian actually isn't my best model. And I'll just, in the interest of time, I'll actually show the second slide where I use, instead, a heavy tail distribution. And it actually turns out to be a better model. This has been known for 100 years, going back to the origins of the student T distribution, which are completely equivalent to the Q Gaussians, or what I call a coupled Gaussian. And in here, as I go to 10 dimensions, my classification continues to perform, and the accuracy of the model stays high based against the Shannon metric, whereas in the previous model, actually as I went to more dimensions, my accuracy actually started to reduce as I was introducing errors in my estimate. And furthermore, it's kind of interesting to note that while 2 features isn't the best in terms of making decisions, which you can see on the right-hand side of low performance, it does have the advantage of being more robust. You're making weaker estimates. Okay, so fine. That's it. That's great.